Okay, so today we are going to continue what we have learned so far until last week. Last week we have learned about couple, the concept of couple, which is basically the extension of the concept of moment in 2 dimension and 3 dimension. And we have learned also about equilibrium and statics of rigid bodies, both in 2 dimension and 3 dimension, uh, which are also related to moments in rotation, etc. Now we are going to start to implement this into structures. So in a structure, when we see a structure is in equilibrium, means it is in static, yeah, it doesn't move. Or when it is in motion but having a constant speed. Okay. So what does it mean? So when a structure is in equilibrium, it means also actually that there are forces and reaction forces between the components of that structure, which makes the whole structure as not in motion, or if it is in motion, not in acceleration. Okay, so in other words, that the sigma of the force, the resultant of the force, and the sigma of the moment of all the components interacting within the structure should be zero. Okay, so in this chapter, as well as in the next chapter, we are going to study about the equilibrium of rigid bodies inside or within a structure, where we are going to study also the interaction between the components of the structure. An example can be given, for example, in our body itself. Okay, when we are not moving, when we stand still, or when we sit still, it doesn't mean that there are no forces inside our body. There are many forces interacting between our bodies, between the bones, between the joints. The bones are interacting with other bone at the joint. So at the joint, there is a force and reaction force. And the resultant of this force and reaction force should be zero, such that our structure does not move. So let's say in the quiz, for example, I give example of a man holding a cup at the at his hand. So it is not moving. It means also muscles and bones are interacting within that hand structure to maintain equilibrium, the force and the reaction force. So in this chapter, we are going to study that interaction. So we need, and we will be able to determine also whether a structure, whether a body or with a component within the structure is under tension, being stretched, or under compression, being compressed, yeah, from the surrounding uh, interfaces with other structure. Now in this slide, let's review back what we have learned so far in the concept of equilibrium of rigid bodies in 2 dimension. So in a particle, when it is in equilibrium, it means that sigma, the resultant of the force should be zero, yeah, in all the axis direction. It means sigma fx has to be equal to zero, sigma fy has to be equal to zero. Then if it is in the 3 dimension, or if it is a rigid body, if it is particle, then it means that only translational equilibrium is required. But if it is a rigid body, means it has a dimension and shape, then we have to insert also the third condition of equilibrium, that sigma moment should be equal to zero. Okay. So first is always we need to draw free body diagram. So draw the boundary of the chosen section and detach or separate it from all the other bodies. If the body has a mass, we need to put a weight equals to the mass times the gravity acceleration, acting at the center of gravity of the body in the vertically downwards direction. Downwards here means to the center of the earth. Okay, so Sometimes this changes when the body is located on a slope. Input all external forces acting on the body. For system involving cables, the force of the cable must act outwards of the body. That is, the cable must be in tension. Yeah, we have learned this in previous chapters. Then put the reactions, yeah, here. Now this is what we are starting to study today in this chapter. Although you have actually done that some question related to this in the quiz. Put the reaction where the body touches or connected to a different rigid body. The free body diagram should also include dimension for the process of taking the moment. Yeah, so in order that we can calculate the moment, then we have to know the dimension so that we can calculate moment equals to force times distance to the point. So when two parts or components interconnected or jointed in a structure, then they could have different kinds or different types of interfaces or interfacing. First, if it is in the form of roller like this, yeah, when it is in the form of roller, it means it can slide in freely at this axis, but it cannot go into the slope. What does it mean? It means that there is a reaction force, yeah, towards the roller. So there is a reaction force. Let's say that reaction force is Ry, for example. Yeah, but there is no reaction force at the plane, on the plane. Yeah? Parallel to the plane, there is no reaction force because it can slide freely. Similarly, also with like this roller like this is not built from small balls like this, but instead one single ball. So there will be a reaction force at the touching point between that roller wheel and the floor. Okay. So there is a reaction force, yeah, depending on the axis. So for example, if the axis is like this is x and this is y. So there is a reaction force vertical from the floor towards the wheel. At the rocker here, similar, it can still slide parallel to the plane, parallel to the slope plane, but it cannot slide into the slope. So it means there is a reaction force also here. Similarly, when we consider a surface which does not have any friction to the to the structure or body or whatever on top of it, then it means that this body can slide easily along the parallel plane to the slope, but it cannot go towards the slope, right? So it means there is a reaction force from the slope into the structure. So the reaction force is always 90 degrees to the surface and towards the body, like this, yeah, 90 degree. This 90 degree. Okay. Now, if the structure is being pinned, okay, pinned into the but it is a collar on frictionless rod. So it means what? The rod here can still slide through this one, yeah, can still slide through this beam, but this rod cannot go in this direction, right? So it means there is a reaction force here, which maintain that collar on that column. Similarly here, this structure can still slide through inside this slot, but it cannot go to the left and right. Yeah, here there is a reaction force from that two parallel beam. So we have here perpendicular to the rod or slot can be directed either way. So you can choose either way, but not both. Now, if it is pinned, the beam is pinned to the what do you call it, to the wall or to the floor, then it has two reaction force. Why? Because this beam cannot move towards the slope, towards the wall or towards the floor, but cannot also move parallel to the wall, right? So in this case, there is two reaction force here and reaction force here. Okay, but it can still slide. It can still go. It can still rotating about this point, right? It can still rotate left or right. So similarly here in a rough surface, it cannot also move. It cannot move parallel to the surface because it is rough, right? The friction prevent it from sliding. It cannot also move towards the floor. So it means there is also two reaction force. Yeah, it's up to you where the direction where you put the reaction force. Later, when we calculate, when we get a negative value, then we know that the actual direction is inverse to the assumed direction. So in these cases, we have two unknown reaction forces. The first one is 90 degrees towards the surface or towards the body, this part. Yeah, this is the first one. Second one is either upwards or downwards, the incline, which depends on the friction force, yeah, or friction force or pin force here. Okay, so okay. Then here now, it is not only pin, but it is completely fixed on the wall or on the floor or welded. So what does it mean? It means that the structure cannot move here. So this one cannot also move in this direction. So cannot move here, cannot move also in this direction. Cannot also rotate this about this point. Yeah? This rotation about that axis point is also not possible. So it means there are three reaction forces. The first reaction force, the second reaction force, and reaction moment. Okay, the AX, here AY, or MA. Okay, yeah, you can assume the reaction moment also as you like, either clockwise or counterclockwise. Later, when we calculate, when we find it negative, then we know that we should reverse the direction. An example here. So we draw a free, there is a structure here having a wheel D, yeah, which is pinned to an L beam structure BCD. The L beam structure BCD has a roller interface with the wall on the left, and that L beam BCD is pinned or connected through point B to a beam AB, right? Who is who is being connected with a weight or a mass M, so means having a weight of M multiplied to G, the gravity acceleration, and that AB beam is being pinned to the floor at point A. So what does it mean? So first we have, it is in equilibrium, so it doesn't move, it is in equilibrium, okay? So what should we do? For example, there is a question, determine the reaction force at C, determine the reaction force at A. How to calculate them? What we need to do is first to draw the free body diagram for the mechanism shown here. Afterwards, we can draw the free body diagram of each of the member of the structure. So in this case, either member AB and then member BCD. First, we draw the free body diagram of the whole structure ABCD, right? ABCD. So the wall and the roof and the wall and the floor becomes the external structure, which, because it is in equilibrium, that external structure will exert reaction force. Okay. So at C, here we know then at C, since there is no, it is a roller interface, okay, it can still slide in vertically, right? It can still slide vertically up and down. However, it cannot move left and right. If it cannot move left and right, it means there is a reaction force at point C to the horizontal direction. At A, it is pinned to the floor. So it means it cannot move left and right. It cannot also move up and down, right? So then it means how many reaction forces are there? It means it has two reaction forces. Okay, two reaction forces. Okay, so then we'll see. So here at the at point C, there is a reaction forces from the wall, reaction force from the wall directed horizontally, because that L beam ABC cannot move to the left. Okay, cannot move to the left. It can also move. It can only slide vertically. Similarly, at point A, or not similar, but a bit different, because now at point A it cannot move right, left, and right. It cannot move to up and down either. So it means there are two reaction forces at A, AX and AY. Then at the middle here, because there is a mesh hung by a rope to the middle of beam AB, so we know that there is a pulling force downward with the value of mass times the gravity, the acceleration. Then if we do member by member, each of the structural member, let's say now we pick AB only. So now the other structures become external to AB. Okay. So AX and AY is similar to the previous free body diagram. It has two reaction forces coming from the floor because it is being pinned. At D here, it has a reaction force from this point. Yeah? So D is this point. Yeah. Yeah. So this is point D. This become points D. Okay. So the AB will feel like that wheel D is pushing towards it. Okay, well, you can also draw the reaction force upward actually, but later you will find, if you find the value negative, you know that the reaction force is pointing downward. It is based on our assumption. Then mg is still the same, the weight pull the beam AB downward, and at point B, so previously we don't draw any reaction force because we consider the whole structure as a one. But now we only take structure AB. So we know that at point B, it cannot move left and right. It cannot also move up and down. So it means at B, there are two reaction forces, Bx and By. Then we can also draw free body diagram at member BCD. Okay, the L beam BC N plus the wheel D. So at B, it will contain reaction forces Bx and By. And if you compare, yeah, with the Bx and By, it's similar, yeah, the previous one, Bx and By at member AB. At C, it will also feel the reaction force from the wall because the connection is through a roller here. So it has only one single reaction force whose direction is horizontal direction. Then at D, it will feel a reaction force from the member AB here, pointing upward from member AB. Okay, so this the free body diagram. Yeah, learning how to draw free body diagram. Now let's go to a more complex and complicated structure like this. We have an M whose center gravity is at G, a mass M, then connected to this two beams, yeah, ACEF and BCD. Both beams are connected in the middle at point C. ACEF is connected to the mesh M through this pin at A, and roller structure at F to the wall. BCD is connected to the structure M at point B through a roller structure, and at point D with pin joints. Okay. Then at point E there is a pulley. Okay, connecting by rope to with a node at BCD. So draw the free body diagram of the whole structure. Draw the free body diagram of just the member BCD here, BCD. Draw the free body diagram of just member ACEF. Draw the free body diagram of member ABG. Where is ABG? ABG, here, the left structure. So how would it look like? Then the free body diagram of the overall structure will be first the mesh at the center of gravity G, yeah, pointing downward. Then at point D, since it is being pinned to the wall, it cannot move horizontally, left and right. It cannot also move vertically up and down. So it means then there are two reaction forces at D, okay, dx and dy. At F, since it can roll on vertically up and down, there are no reaction forces in vertical direction, but it cannot move horizontally towards the wall, right? There is a reaction force from the wall. Here we draw it F pointing leftward. Then at D, at E, since the whole structure is being pulled by this pulley to the right, so we have to draw this external force T, also pulling from this point. Okay. So if you ask why didn't we draw also the pulley force in this between this point and this point, the answer is because in this overall free body diagram we only consider the reaction forces coming from the external structure of this structure. We do not really yet consider the structure inward, the forces inward, the force within the structure itself. That we will consider when we consider the free body diagram at each member. For example, here at member BCD, the point B is has a roller structure, yeah, related to the structure ABG, yeah, ABG here. This is a roller structure, so it means it has only a single reaction force horizontally towards the roll, towards point B. At C, since it is being pinned, C is here to the other beam. It cannot move vertically, cannot move freely vertically, cannot move freely also horizontally. So there are two reaction forces, Cx and Cy. Then at D, similarly, it is being pinned to the wall here. See, being pinned, the D is being pinned to the wall. It cannot move vertically, nor can it move horizontally. So it means there are two reaction forces, dx and dy. Here. Then at this point, yeah, this point, since it is being pulled by this rope through this pulley structure by a force of T, so it means this rope, this point is also being pulled with a force of T to this in this direction, yeah, not completely vertical downward, but with some angle. What about the free body diagram at ACEF? Similarly at A, since it is being pinned yeah, to the structure ABG, so it has two reaction forces AX and AY. At C, similar to the previous structure BCD, it has also CX and CY, two reaction forces. Now at E, here, it is being pulled in two directions. Yeah, because it is in tension. The rope is always in tension. The first direction is to the right. Yeah, to the right, and the second direction is upward, yeah, towards this the other beam. That's why we draw here two T. One T is upward, a little bit to the right, and the other T is to the right, horizontal T. Then at this point, since it cannot move horizontally, it means there is a reaction, there is a horizontal reaction force from the wall. Then free body diagram at the member ABG. Here we have B here, okay, because it is being connected through a roller, so it cannot move horizontally. So it means there is a single reaction force at point B. At A, it is connected with pin connection, pin joint connection. So it means it cannot move horizontally, nor can it move vertically. So there are two reaction forces, AX and AB, AX and AY. Then there is a weight at the center of gravity of this G, yeah, with the value of mass times the gravity acceleration. Okay, so after we draw all the free body diagram, then we can determine the forces using the equilibrium, the equation of rigid bodies. Yeah, first, of course, the free body diagram must be drawn for every solution. Moments can be taken from any point within the body, within the structure. Even you can take the moment about another point outside the body. It is possible. As long as later as it is in equilibrium, means it doesn't rotate, right? Sigma moment should be 0. So the three equations used may not necessarily be sigma fx equals 0, sigma fy equals 0, sigma ma equals 0. Moments can be taken twice or thrice. For example, sigma fx equals 0, then you use sigma m about sigma ma equals 0, sigma mb equals 0. Moment about point A equals 0, moment about point B equals 0. You can also take sigma fy instead of sigma fx. Sigma fy equals 0, then sigma moment about point A is 0, sigma moment about point B is 0. Then you can take even three different equation moment from moment equation. Sigma moment about point A equals 0, sigma moment about point B equals 0, sigma moment about point C equals to 0. Let's take an example here with value, with number. Determine the reaction force at A and D here of the rigid body shown in this diagram. Okay. So at A, since it is pinned, yeah, pin means it has two reaction forces, AX and AY. At D, it is roller. It means it has only one reaction force at this direction, yeah, vertical 90 degree towards that surface. Okay. So here AX is AY. There is a force from the left. It is 80 Newton. Then from up is 50 Newton at this point. Yeah. So here there is a single reaction force actually, perpendicular to the surface. However, then we can resolve this into two components. The x component, dx, equals to d sine 30 degree. Yeah, so let's see drawing. Let's draw. The surface is like this, right? So this is 30 degree. So it means this equals to this is 90 degree. Okay, 30 degree. So this is 90. 90 plus 30 is 120. So this is 60 degree. So it means this is 30 degree, right? This is 30 degree. So this component dx equals to d sine 30 degree, right? This is basically similar like this component. And this one dy equals to d cosine 30 degree. Okay. Do not be mistaken. Yeah. Sometimes you put it in the reverse meaning. So dx equals to d cosine 30, dy equals to d sine 30 degree. You have to look at where 30 degree is. Okay. Be careful. Okay, then continue further. Let me drawing. So use this formula: sigma fx equals 0, sigma fy equals 0, sigma moment about point A equals to 0. Where is point A? Point A is this point. Okay, about this point equals to 0. So from here, sigma moment about A equal to 0. Yeah, then 0 equals to 50 Newton meter times 1 meter. So this part, yeah, 50 Newton meter multiplied by 1 meter clockwise. That's why it is positive. Plus 80 Newton meter times 0.3 from where? From this part. Okay, this will rotate also clockwise about point A multiplied by this distance 0.3 meter. Negative d cosine 30 degree. Negative this one negative. This is d cosine 30 degree. So at this point, which multiplied by 1.3, where is this one, the total here, the distance from this point to this point is 1.3 negative 0.8, right? The distance from the x, sorry, dy here towards point A, negative because it is counterclockwise. Then d sine 30, the dx will also rotate this counterclockwise. So the distance is 0.3 plus 0.5. Yeah, here, 0 or 0.8. Okay, so from here we obtain the reaction force at B, 88.8 Newton. Then using sigma fx equals 0, we obtain AX. Using F sigma Fy equals 0, we obtain AY. Okay, negative 61.8 Newton upward or 61.8 Newton downward. So the resultant of A will be the square root of AX square plus AY square. We obtain 71.3 Newton. The angle of the reaction force at A is the arctangen of AY divided by AX. So equals to 60.08 degrees. Okay. Yeah. Now, this is not that easy. Okay. So let's do this exercise. We try to do this exercise and we will discuss about it in the second hour. Okay. So I will stop.